The cumulative hazard functions and the mean residual life functions for the gamma distribution are also mathematically intractable. In fact, the only thing we can do is we can go to the 5 by 5 matrix and simply write down the cumulative hazard function as the opposite of the natural log of the survivor function. And again, to the 5 by 5 matrix, you see that the mean residual life function can be written as a function of the survivor function. So that's the bad news with the gamma distribution. The lifetime distribution representations are not particularly tractable. On the other hand, the moments are fantastic. There is a result for the gamma distribution that says the expected value of T sub r is this quantity. You can see there is a product in the numerator and then lambda raised to the r power in the denominator, and that is for integer values of r. When you plug in r equals 1, you get the population mean. When you plug in r equals 2 and use the shortcut formula, you get the population variance, sigma squared. When you take sigma divided by mu, you get the coefficient of variation. And again, you plug in 3 to a little bit of algebra, you get the population skewness, and you plug in r equals 4, a little bit of algebra, and you get the population kurtosis. Not surprisingly, with those nice mathematically tractable moments, you also have a nice moment generating function, and it is lambda divided by lambda minus s raised to the kappa power for s less than lambda. In addition to the exponential special case of the gamma distribution, and of course that corresponds to kappa equals 1, there's two other special cases that are of interest. The first is the Erlang distribution, and the second is the chi-square distribution. The Erlang distribution applies when kappa becomes a positive integer n. And when that's the case, the probability density function looks like that. Notice that the gamma function from before has now become a factorial because we have an integer argument n. The survivor function for the gamma distribution, if you remember before, was written in terms of an incomplete gamma function. Well, this is clearly much better. Now it's being written as a summation, so that's an improvement. Here are some applications. First of all, the Erlang distribution is the sum of independent and identically distributed exponential random variables, and here's how that's stated formally. If T1 through Tn are mutually independent and identically distributed exponential lambda random variables, then their sum will have the Erlang distribution with a scale parameter of lambda and a shape parameter of n. This is appropriate for modeling the failure time of a standby system with n components. In that particular situation, you have to assume that sensing of failure is perfect and immediate, and also switching from one component to the next is perfect and immediate. The Erlang lambda n distribution also models the time of the nth event in a homogeneous Poisson process with rate lambda, and we'll see more of that in Chapter 6. Finally, when n is equal to 1, it's not surprising that this will collapse to the exponential lambda distribution. The second special case of interest is the chi-square distribution, and that applies when the scale parameter takes on the value 1/2 and the shape parameter in the gamma distribution takes on the value n over 2, where n is some positive integer. That n, which is the positive integer, is referred to as the degrees of freedom. The chi-square distribution shows up in statistical inference concerning the variance in classical statistics. It's also going to show up in inference concerning the exponential distribution when we look at lifetime data out in chapters 7 and 8. When n is equal to 2, that's the one value of the degrees of freedom where the chi-square distribution collapses to the exponential distribution. So there you have two special cases of the gamma distribution that will show up in the future. You may have observed already that when the Weibull is good at one thing, the gamma is not so good at another, and we're going to go through those dual relationships, but before we do so, here is a result concerning sums of gamma random variables. So if Ti has the gamma distribution with lambda and kappa sub I for I equals 1 to n, in other words, they all have to have the same scale parameter, and they are independent, then when you add them up, it stays in the family, that is gamma, with parameters lambda and a shape parameter, which is the sum of the component shape parameters. The proof of that result is done by moment generating functions. So here are these dual relationships. The properties are given down below here. For the Weibull distribution, you have a nice tractable hazard function. In the gamma distribution, you have a very mathematically intractable hazard function. It involves computing the incomplete gamma function. The moments on the gamma distribution, we saw those a slide or two ago. Those are very tractable. The moments on the Weibull are really messy. So one is good at one, the other is good at the other. Self-reproducing property. That property said minimums of that random variable have the very same distribution. And in the case of the Weibull, when you fix the shape parameter, you have the self-reproducing property, but for the gamma distribution, you don't have the self-reproducing property. Finally, the last property here are sums. The sums of Weibull random variables do not have the Weibull distribution, but sums of gamma random variables do have the gamma distribution. That's given up above here when you fix the scale parameter lambda. So that completes three distributions in detail: the exponential, the gamma, the Weibull. And now what we're going to do is go quickly through other distributions that show up in lifetime data analysis.